Okay, in section 5.5, we will talk about electric and magnetic field system. And in this section, we will illustrate the determination of the low frequency terminal behavior of a physical structure in terms of the quasi-static extension of the static field concept. Well, that's the a very important and fundamental difference between circuit theory and transmission line circuit theory, or the microwave circuit theory. Okay, so the circuit theory, the conventional circuit theory, can be regarded as a low frequency approximation of the electromagnetic theory. However, the circuit theory develops way earlier than Maxwell equation. So as a result, when we talk about microwave circuits, we use terminologies that are developed in the circuit theory. Okay, so we will use the so-called inductors, conductors, resistors, such kinds of circuit components in our transmission line circuits. We will use those conventional components. However, in this section, we will try to explain the difference between conventional circuit theory and transmission line circuits. The quasi-static okay, the first thing is the circuit theory can treat the DC signal as well as low frequency signal. It can deal with time variant signal. For example, we have capacitance and inductance. Okay. For capacitance and inductance, if you look into the relationship between voltage and current signal, you will see that the inductance is related to the time derivative of current, while for capacitors, you have a time derivative of voltage in your capacitor relationship between voltage and current. So conventional circuit theory, or we should refer it to lump circuit. 传统的电路学有时候又叫做 lump circuit 那微波电路的话就是 microwave circuit 或者是 transmission line circuit 所以虽然 transmission line circuit 是从传统的电路学 lump circuit 所发展而来的，但是他们会有一些基本上的不同，那当然这是我们在后面这几节里头要去解释的Okay, so lump circuit theory can treat time variant signal, time variant voltage, time variant current. However, they have some limits. They have some limits. The limit is referred as the quasi-static approximation. It can only treat frequency up to the quasi-static approximation limit. So we will learn today how to find out the limit of the quasi-static approximation. Right? So that would be the footnote here is that the quasi-static field means that we're taking one first order approximation of the signal within the circuit. Okay, so the lump circuit will can treat DC signal as well as first order time variant signal. So here let's check up with a structure. This structure is Can you tell, is that an inductor or a capacitor? In the textbook, it refers as an inductor. Because, however, I think this one looks like a capacitor, right? Now you have a parallel plate laying horizontally. However, at the very end, the right end of the two plates, you have another vertical plate that connecting the top and bottom plate. So it's referred as an inductor. However, imagine that you are a small ant, and this is a relatively large structure. Now, you step into this position, okay? You are a small ant with a good eyesight. So if you look up, you see there is a top plate on the top of your head, and there's another plate underneath your foot. So do you think this is a capacitor or an inductor? If you are a small ant, okay? If you're a tiny little ant, I might think this is a capacitor. So it should show some capacitive behavior for me, all right? For this ant. On the other hand, if you are, junior students in the college, so okay, you just look at the slides over here. You see, oh, it's connected in the end. It's connected, the two plates are connected in the end. So this is an inductor. All right, so again, the behavior of this structure, the electrical property of this structure may depend on how big you are, right? Or put it this in another way, it depends on the wavelength of your signal, or it depends on the frequency. If the signal frequency is relatively low, which means the wavelength is very large, larger than this structure, larger than the dimension of this structure, then this structure shall look like an inductor to this low frequency signal. On the other hand, if the wavelength of the signal is relatively small, much smaller than the structure dimension, or if the frequency of your interested signal is relatively high, so it comes with a small wavelength, then this structure may look like a capacitor to this structure. Okay? So, yeah, the performance characteristic of a circuit component is dependent of the frequency. Taking, here's another example, a battery. A battery can be regarded as a very large capacitor, right? Because it stores positive and negative charge on the two ends of the battery. Okay, so it can be regarded as a large capacitor. So if you check up the impedance of a battery at the DC or very low frequency range, it shall exhibit capacitively property. It shall exhibit properties similar to a capacitor. However, if your test frequency is increased, and then at a certain point, the effective impedance of the battery will become inductive. Okay? And if you keep increasing the test frequency, then you will find that at a certain point, the battery will turn from inductive to capacitive again. And then if you keep increasing the frequency, then you will become inductive again. All right? So the characteristic, the impedance of, well, not only a battery, not only for any component, any circuit component, we are alternating between capacitive and inductive. So it depends on the frequency of your test signal, all right? But for low frequency, for DC signal or low frequency signal, you can judge the property, you can judge the components to be, you can decide the component to be capacitive or inductive according to the geometry. Okay? For this example, at a low frequency, it looks like it should be an inductor. Okay? So therefore, why you have a difference like this? Why the same structure behaves as a capacitor, it behaves like an inductor at a low frequency and becomes a capacitor at a high frequency? The size matters. Okay? So depends on the test signal wavelengths. So think about that. And the other important concept is propagation delay. Propagation delay. If you are high frequency, then if you use a high frequency signal to explore, to probe, to examine the structure, well, it may take a while to know the overall performance feature of the structure. I will explain about that later. Okay. So let's keep going with this structure. So because this thing is inductive structure in the DC range, so the test signal is now is a DC current source. Okay, you see this arrowhead, meaning that it's a current source. A constant current source. Okay. So if we neglect the fringing, so if this is a current source, constant current source, what happens with this structure? It will provide currents flowing on this plate structure with clockwise current, right? Clockwise flowing current. Then, what is the direction of its magnetic field? Using the right-hand rule, if you have a clockwise flowing current, the corresponding magnetic field is pointing into the screen, like the crosses here, right? Okay. And what does that mean? No fringing field in this region. So here we see here is a current flowing from right to left, from left to right. Here we have current flowing from right to left, and at this point there's no current. Does that mean there's no crosses? There's no fields in this location? Well, the reality is, yes, you shall have some magnetic field at these locations. And they are referred as the fringing field. 霸气外露有没有听过？那个磁场会侧漏一些跑出去但是量不多啦所以可以忽略Because the amount of the fringing field is not that much. And when you calculating the overall performance of this structure, the fringing field does not make much difference. So therefore, to simplify our analysis, we assume that there is no fringing field at the boundary. All the fields are confined within this, confined in this, within this structure. Okay, and okay. Right here is an important thing. Is there any voltage difference in the right-hand side of this structure? No. Because there is no electrical field intensity in this region. However, this plot is labeled with V here, which means at the opening, you should get some, you should build up some, this structure will build up some voltage at the left end. This is not true for DC signal, right? This is not true for DC signal in the steady state. Okay. However, in the so-called transient behavior, I mean, the transient behavior implies that if you just close the circuit and it tries to build up currents in this structure, then you may observe voltage at the opening. Okay. We will see this in following slides. For a constant current source of a value I sub 0, it drives the structure at the end of Z equal to minus L. So the width or length, now let's go back here a little bit. So here we define it as Z equal to 0. So Z here the coordinate for the on the Z-axis is Z equal to minus L. So the length of this structure, of this metal structure, is L. Okay. The width of this structure is W. Okay. So the total currents provided by the current source is I. Then the surface current density, J, can be calculated as I divided by W. And note that the height of the two plates, the top plate is defined as X equal to 0. The bottom plate is defined as X equal to D. Okay, so the X-axis is pointing downward, right? 任何时刻你看到那个 XYZ 轴的时候记得做一件事情，拿起你的右手，稍微比划一下。有人是会画错的，根据右手定则去看那个 XYZ 轴的顺序，真的有人会画错。我在审论文的时候，有人投稿投论文，那个 XYZ 轴画的是反的，这种事情都会发生OK， 所以自己检查一下Alright, so for the top plate, X equal to 0, the current direction is flowing from left to right, which is in the positive Z direction. On the other hand, at the bottom plate, which is located as X equal to D, the current direction is flowing from right to left in the minus Z direction. So it's labeled as minus I sub 0 divided by W. And the current is uniform across the Y direction. And as you can see here, you have a clockwise current flow, which produce a magnetic field flowing in which direction? Positive Z direction, positive Y direction, right? Okay. So here is our problem setup. And as you can see, the magnetic field is flowing to the positive y direction, and they are distributed homogeneously, uniformly inside this structure. Why? Because they are produced by top and bottom current. They are the same everywhere on the top plate and the bottom plate. So the corresponding magnetic field, magnetic flux, is homogeneous within this space. And they can be expressed as this, which is derived from the Ampere-Circuitial law using just the first term on the right-hand side. The closed loop integral of the magnetic field is equals to the total current enclosed by the loop. Okay? Well, for this computation, for this calculation, you should not look at this plot, because the closed loop is not this. The closed loop is this one. 这边要搞清楚哦，这边要搞清楚哦，重要哦。So you draw an imaginary loop around the top plate or the bottom plate. Okay, at the opening or inside the plate, both inside and at the opening are okay. Okay, you can draw it anywhere. But so as you can imagine, the left-hand side of the Ampere-Circuitial law is what? Is closed loop of the magnetic field. So the magnetic field must be parallel to the loop of the observation loop. So in this rectangle, which path is valid for the closed loop integration? Only the line that is located within this inductor structure, right? On the outside or the vertical ones do not experience any magnetic field. On the other hand, in the inside, the magnetic field H goes this way, which is parallel to the loop. So you can find out the closed loop integral of this as W times H, and it should equals to the total current that is passing through this red rectangle, right? So what is the total current passing through this red rectangle? J sub 0 times W, right? The currents on the top plate going from left to right. So the total current is, well, I sub 0. So I sub 0 divided by the length W end up with the magnetic field expression within this inductor structure. Okay? So you should know how equation 5.84 is derived. So as you can see the result, the magnitude of the magnetic field and the current density Js are the same. They are exactly the same because of this relationship. However, even though the magnitude are the same, the direction of H and J are not the same. They are in fact perpendicular to each other. Okay? H is in the positive y direction, while J is in the positive z direction. So that's another thing you need to be careful with. Okay? So anyway, here we have the H, the magnetic field intensity. So we can derive the magnetic flux density. You just need to perform a multiplication of the permeability mu. Then you end up with B. Then the next thing is calculate the flux, magnetic flux, passing through this area, this structure. Because magnetic field is going this way, so the total flux in this region can be computed as the surface integral of this distribution. And because H or B are homogeneous across this ray rectangle, then the surface integral can be computed easily by taking the product of By, well, you only have the By term, with D times L, that is the area of this ray rectangle. So substitute the expression for By, you ended up with this expression. And here is the total magnetic flux passing through your inductor structure. And then we can derive the inductance of this structure, which is according to the definition of the inductor, which is the ratio of phi over total current I. You end up with mu times dl divided by W. So as you can see here, the inductance of this structure is related to the geometric parameter, including the length, width, and depth. Okay, length, width, and depth, as well as material property. Here we see the inductance is proportional to the permeability mu, which means if this is originally air, you can fill this structure, fill this cavity with ferrite, which has a much larger permeability. So it can effectively or substantially increase the inductance of this structure. That's the reason why if you open up your personal computer, you see the motherboard. 台湾国语是叫主机板啊，英语叫母机板motherboard， 我不知道为什么这样。You look at the motherboard, you can identify the inductor, right? You have some circular ferrite or cylindrical ferrite, so you can wrap the wires around it to form large capacitor. So the purpose of the ferrite are to boost or to increase the inductance of the structure. All right, so let's stop here. We'll take a break.